15.2 talks about double integrals over general regions, so we did it over rectangles. Suppose we have a region instead of a rectangle. So suppose this is z equal f of x, y. It's kind of like that surface up there, and the shadow of that on the ground is really over this region, R or D, whatever you want to call it. And if I put a rectangle around this, I'm really looking, because I know how to do a rectangle, what I do, I say, well, let's set f of x, y, let's set capital F of x, y to equal f of x, y, the function itself, if the point x, y happen to fall in that region D, and 0 otherwise. What that does, that really takes out the rectangle and keeps us with D. Now if I take this D and I map it on the X and the Y, I'm looking just on the shadow on the ground. This is A, this is B, this is C, this is D. Now if I want to find the area of that region, I could do that two different ways. I could say so here I could say the double integral over region D of f of x, y, dA is actually the double integral over rectangle of f of x, y, dA. I could do two ways to figure out what this is. That is, I could say I'm gonna look at this from the x perspective, meaning drawing vertical asymptotes or vertical cross sections, right? Or I could look at this from the y perspective, as you did in your first semester calculus, and I could draw a delta y, and here I could draw a delta x or a dx. So the book refers to this as type 1 region. You really don't need to know that. And this is type 2 region, and they might ask about that on the homework. No need to worry about that. Just remember, type 1 is really our traditional dx, and type 2 is our traditional dy. Now, if I want to find this area, I could say this is the integral over region D of f of x, y, dA. If I am certain that this is always positive, so if I am certain that f of x, y is always bigger than or equal to 0, then this would be volume, finding the area of the base times the height. Area of the base is right there, and the height is really this. I could say I'm gonna take dx type 1. So what I do, I integrate, not red, let's go with blue. I could integrate with respect to x from a to b, right there. And I would say then, y is gonna run, I'm gonna call this the g1 of x, and I'm gonna call this the g2 of x. Y would run, and the way it works, you would take vertical. Where do you start? Where do you terminate? Where you start is the lower limit of the integral. Where you terminate is the upper limit of the integral. Of course, if I want volume, this is the area. I have to multiply it by the height, and the height is f of x, y, or z. Or I could say, you know what? Instead of doing that, I'm gonna switch things around. I'm gonna really run from with respect to y from C to D. That means x is really gonna run, it starts right there and terminates right there. So here, I'm looking at this sideways. I'm gonna call this h1 of y, and this is h2 of y. So where you start will be the initial, and where you terminate will be the endpoint. That's the area. If I put nothing there, that's the area. If I give it a height, that becomes volume. Now, not to worry if you're not seeing this clearly, because all of our next set of examples are going to work over what we just did right now. So let me start with the first set of examples. First set of examples says, set up an iterated integral for the double integral of a region R, where R is given in part A by the following. Use both. So set it up both ways, and this is a good way for us to really get the hang of this. So we need to be able to see the region. I want x to run between 0 and 3, 0, 1, 2, 3, and y to run between 0, y equals 0 is right there, and y equals 3 minus x, 3, rise 1, run 1. So we're talking about a line, and we're cutting that between 0 and 3. So we're really talking about that region R. If the book says use type 1 and type 2, just remember type 1 is really with respect to x, type 2 with respect to y. On a test, I will never say that. I'll say both cross sections, vertical and horizontal. So according to the book, this is type 1 and this is type 2. Well, if I want to set up an integral that would find such a region, what I'll do, I'll say, all right, I'm going to take the integral and I'm going to start, let's say, with x first. If I'm starting with x, this is really what I'm viewing. I'm viewing x running vertically. X runs from 0 to 3. Then y is going to run, because my width is right there. Y is going to run. Where does y start? Y starts at 0. And if I put an arrow, where does y terminate? Y terminate at 3 minus x. Or I could look at this the other way around. I could say, let me start with dy first. Well, if I start with dy, y runs from 0. It happens to be 3 as well. And x is gonna run, so now I'm running sideways, right? X is gonna run from 0. This is the line y equal 3 minus x, but I need to know what x equal. Doesn't that mean x equal 3 minus y? Okay. It looks as if you could switch those around with ease. I'm just picking a very simple problem to start with. Of course, you're going to integrate those on the homework. I'm more interested in the setup than anything. Now, the next example is a bit different. It's not as straightforward as the first example, but it's the same idea. So, if I wanted to look at this, I know that x runs between 1, there is 1, and e is 2.7 squared. Let's say it's right there. So x is between those, infinite of course. Now, if you look at the y runs between y equals 0 and y equal natural log of x. Natural log of x is a graph that looks like this. No need to make it longer. Here we go. Now, if you put e squared in there, you will get a 2. I want it to look a bit nicer. There we go. Now the graph continues, but I am interested only in the region between 1 and e and 0 and the graph. So this is really what I'm looking at. This is the equation, y equal natural log of x. So let's go with the traditional. If I take the double integral over region R, where this is R, of dA, that's going to be the integral. Let's go with x first. X is going to run from x equals 0 to x equal e squared. Y is going to run from 0 to natural log of x. That's simple. Well, what if I wanted to reverse the order? What if I wanted to run with respect to y first? I noticed that y is going to run from 0 to y equal 2. And x is going to run from the curve. If y equal natural log of x, what does x equal? Isn't that e to the y? And where does x terminate? X terminates at e squared. So just make sure that you solve each equation. You cannot have a dx and an x in there. It has to be x equal. And you can't have a dy and a y there. It has to be y equal. Now, make sure that when you're finding an area, the outsidemost limits are numbers. Otherwise, you've got an expression which is not what we want. And what if I wanted to look at this graph? What if the region I'm looking at is actually y equal e to the x is a graph that looked like this. I'm looking at this graph having y run between 1 and e to the x. Okay. And x is running between 0, x equals 0, and x equals 3. So which region do you think we're talking about? So I was going to say, if you are to look at the x first because you're used to it, let x run between 0 and 3, that's this rectangle. But y runs from y equal 1, y equal 1 is right there, to y equal e. Y equal e is right there. So we're talking about this region. Well, if you take the double integral over this region R of dA, that would be the integral, and let's go with x first. X runs from x equals 0 to x equal 3, that's simple. And y runs from 1 to e to the x. Seems really straightforward. What if I wanted to reverse the order? What does y run from? Well, if I want to do this sideways, y runs from 0. If x equals 3, what is this point? So y runs from 0 to e to the third, and x runs from, what does x equal? If y equal e to the x, isn't x natural log of y? And where does x terminate? At 3. So that's how we'll do this. I'll pick this up in the next video.